All right, how are you guys doing tonight? Good. Cool. So tonight, we're going to talk about real split power supplies. Remember last time we talked a little bit about power supplies, and we laid out the block diagram for them and the general parts. And we talked about everything except for the last part, which was the regulator. So tonight, we're going to talk about the regulators, and then we'll let you guys actually make some of your own power supplies that include regulators, so you get that nice, clean DC output that we're looking for. And we'll see that the regulators we're using are called linear regulators. In other words, they're analog regulators. Next time, on Thursday, we'll actually get to see a different type of power supply, which is called a split mode power supply that actually has a digital regulator. So we'll get to see that on Thursday next time. So we're going to start with a brief review. We'll talk a little bit about the diode homework. I know I said last time we would try and do some problems from the homework, but then we had Tiffany come and she gave us that great presentation, and we didn't have a lot of time for the homework problems. So tonight, I'll start off with some homework problems. I'm happy to help anybody who has questions about those. Then we will review the block diagram for power supplies, showing what components are in every power supply. And then we'll talk about some of the rectifier types that we discussed last time. Then we'll go on to the lecture for today. We'll talk about the last component, like I said, regulators. We'll talk about some of the different types of ICs, integrated circuits, chips, in other words, that provide regulation. We'll see how Zener Diodes can actually be used as simple regulators. And then, like I mentioned, next time we'll talk about split mode power supplies. And then we'll go and do a preview of today's lab. So we'll review electrolytic capacitors. We'll talk about a bridge rectifier integrated circuit. This is neat. You guys remember last time you built your own bridge rectifiers out of 4 diodes, and you guys all did it, which was awesome, but it was kind of a hassle, right? You have to get all those parts in the right place. So a lot of people have had the same problem, and some companies saw this as an opportunity, and so now they make little chips that have the rectifier built into them. Nice. So we'll see how those work, and you get to actually use those tonight, so you won't have to build your own bridge rectifier. And then we'll remind ourselves a little bit about how to use AC coupling on the scope, because that's going to be useful tonight to measure the ripple voltage in your power supply. And then finally, we'll talk about half-watt resistors and why those are important for tonight's circuit. Any questions before we get started? Okay, cool. So then let's do a quick review of the diode homework. Anybody have any trouble with the diode homework? Anybody have any problems? Yeah, sure. Number 7? All right. So, what page was that on? 17, 18.
Oh, nice.
All right. So number 7. Okay, so that's the circuit that we have. And then we have to find the voltage of the Zener diode, the current of the Zener diode, the voltage for resistor 1, this is 1 and this is 2, the voltage for resistor 2, the current for resistor 2. Man, you got the hardest one. Good job. All right.
That was the plan.
Yeah, that's good. That's good. I'm glad you're thinking ahead. All right. The current for resistor 2 and the total current. And it says that the Zener voltage is 3 volts. Okay? So, since it tells us the Zener voltage, we can write that down right away. All right. So, we've got 3 volts there. All right. So then, how much voltage do we have across this resistor? Yeah, 3 volts, exactly. This diode is in parallel with the resistor. And you remember when things are in parallel, the voltage stays the same. The current might be different, but the voltage stays the same. So if we have 3 volts on the diode, we also have 3 volts on the resistor. Another way to think about this is that we know that this is ground down there, so that's 0 volts. We go up by 3 volts, so we have 3 volts at that point. And remember that the voltage is the same all along any wire. Okay? So if we have 3 volts there, we have 3 volts over here, and how much voltage do we have over there? 3 volts also. Yeah. So we've got 3 volts all along this wire, and we have 0 volts there. So if we have 3 volts on the top and 0 volts on the bottom, that's a difference of 3 volts across the resistor. Okay. So we can write that in right there for the voltage on that resistor. Now we have to figure out the voltage on resistor 1. And it's the voltage across resistor 1, right? Mm-hmm. So that's the difference between the voltage on one side and the voltage on the other side. So we know that we have 0 volts down here. Then we go up by 8 volts. So how much voltage do we have right here? 8 volts. 5. Yeah, exactly. So we have 8 on one side, 3 on the other. The difference is 5 volts. So that's the voltage across resistor 1. Okay. So okay, so now up here we know that we have 5 volts and we have a 1 kilo ohm resistor. Can we figure out the current for that resistor?
Yes.
Yeah. So what law can we use to figure out the current?
Ohm's law.
Ohm's law. Right. So remember, Ohm's law is written like this. So we just cover up the thing that we want to figure out. We want to figure out current in this case. So we cover that up. We see it's V over R. So that is 5 volts over 1,000 ohms. That comes out to be 0.005 amps or 5 milliamps, right? So we got 5 milliamps flowing through there, through the Zener diode. Now, over here, with this resistor, we can do the same sort of thing, right? We know that we have 3 volts across the resistor. It's a 1 kilo ohm resistor. So we can do the same calculation, except now the voltage is 3 volts. Yeah, so it comes out to be 3 milliamps. Now, oh, yeah, I put this in the wrong place. I'm sorry. This was the current through resistor 1, which is also the same as the total current. So if we have 5 milliamps there, we have 5 milliamps coming out of our power supply, and that's the total current. So we know the total current is 5 milliamps. So what we know is we've got 5 milliamps going there, and then some of it goes down there, and some of it comes around this way. So 5 milliamps flowing into the junction. How much of it flows around this way through the resistor? Yeah.
So 2 goes across the
Exactly.
Zener.
So we have 3 milliamps going out that way. Whatever's left over has to go down that way. So that has to be 2 milliamps.
So Zener LED has resistance, and regular diode doesn't have resistance, but it's this one.
Well, okay, so
Or it's just the home. I mean,
so it doesn't work quite like a resistor. It doesn't make it. So it's not like a wire. A wire essentially has very, very small resistance. So no matter how much current you put through it, it has a wire has very small resistance. Resistors can have medium or large resistance. A Zener diode doesn't behave either like a very small resistance or a large resistance. It behaves in kind of a fundamentally different way. So this is a 3-volt Zener diode, so it's always going to have 3 volts across it, regardless of whether I put a small, a tiny current through it or a big current through it. So it does resist the flow of electricity somewhat, but it doesn't behave just like a normal resistor.
so we are not calculating resistance of diode at all, or
Right. I mean, there's no calculation for a resistance for the diode.
No, because sometimes, like, if you look at other examples, find this and that, and you're like, okay, I need a resistance, to find current or whatever, and may I use this to the diode, to find other components in the circuit, which you cannot use any resistance to any diodes.
Right. You can't just say this diode has a 100 ohm resistance.
Okay.
It doesn't work that way. Yeah.
Can you move a little?
Yeah. Are there any other questions about this one before we go? Yeah.
Well, that's lower bias.
Good question. So this has a positive voltage there and a negative voltage there, so it is reverse biased.
Okay.
Yeah. So if the Zener diode had been forward biased, how much voltage would you have across it?
0.7.
Yeah, about 0.7 volts. So Zener diodes and regular diodes all have about 0.7 volts across them, 0.6, 0.7, somewhere in there, when they're forward biased. When they're reverse biased, that's when Zener diodes have their specific voltage across them. And plain diodes,
Zero.
well, they don't let any current flow. Yeah.
That's zero.
Well, no,
Regular.
they can have actually a lot of voltage. If this had been, yeah, they can have a lot of voltage. And maybe we'll see that in one of the other examples. So other questions about this one? Okay. So, number 11 is what I heard. So we've got 5 volts this time, and then resistor, diode, and this is actually an LED in this case. And then we're going to assume that the LED has a voltage of 1.5 volts across it when it's forward biased. This is positive voltage there and a negative voltage there, so it's forward biased. Remember, LEDs can have more than 0.7 volts across them. They typically have 1.5 to 3 volts, depending on what color they are. So this one has 1.5 volts across it. And we have to find the resistor so that you get 20 milliamps flowing through the circuit. Okay? So let's see how we can do that. So we know that we're starting at 0 volts down there, and we go up by 1.5 volts. So what voltage do we have there?
3.5 volts.
Well,
Never mind.
yeah,
Other way.
1.5.
Thinking backwards.
Right, you're ahead of the game.
Yeah.
So we have 1.5 volts there, and here we go from 0 volts up to, we go up by 5, yeah, so we get to 5 volts. So the voltage across is what you said, Margaret,
3.5.
3.5 volts across that resistor.
You should divide that by 20 milliamps.
Yeah, exactly. So again, we can use Ohm's law to figure out the resistance. So we say Ohm's law is like this, VIR. Here we want to figure out the resistance. So we cover that up. We see that it's V divided by I. So that's 5 volts divided by 20 milliamps. Now, can I just divide 5 by 20 like that?
No?
Right. I can't just do that. I have to convert into raw units first. Yeah, so 5 over 0.02
175.
amps.
175.
175?
Oh, 5. I'll
Yeah.
divide it by 3.5.
Oh, you're right. Thank you.
Yeah.
Thank you. Yeah. Right, it's 3.5 volts across the resistor. So 3.5 volts divided by 0.02 amps is 175 ohms. So
I could do it.
resistance is 175 ohms. Yeah. What's that?
That's this question.
Good.
So LED has a light and
Right.
has no resistance.
Well, it resists the flow of electricity, but it doesn't have a constant resistance. How about that?
How does it?
So it doesn't have like one
I'm
number.
not getting it because it's giving light. That means it has to be resistant. Because
Right.
otherwise, why is it light up?
Right. So it resists the flow of electricity, but that number can change. So let's
So
do
you're
an
saying it's
example.
like not constant
so-
resistance.
Yeah, exactly. It's not constant.
So we can't even count because on my calculation, I found that diode has 75 ohms.
Right. Sure. Okay. So
Because if you can find total resistance, right? If there was a question of this,
right.
then it's like, okay, if LED is consuming amperage and voltage, then it should have a resistance. Or we not including even LED resistance in total resistance.
Well, okay.
Of the
So
circuit.
let me show you what I mean. So you're right. So this has 175, or I'm sorry, we have 20 milliamps, we have 5 volts. So if we were going to do it that way, we would say that R total equals V total over I, so that's 5 volts over 0.02 amps. So that comes out to be 250 ohms. So then the resistance of the diode in that case would be yeah, 75 ohms. Okay? So in that case, the resistance came out to be 75 ohms. But let's try something else.
Oh, I was gonna say, if you change the voltage on there, would that change the?
Yeah. So
Yeah.
let's see what happens if we make this 2 volts instead. Okay? So now we have now we have 2 volts over there. Over here we have 1.5 volts. So we only have 0.5 volts across there. So then
25.
We would have to keep the
actually,
resistance.
right. So
That'd
let's
be the constant number. That'll also be a constant number.
let's keep the resistance the same. So we have 175 ohms. So we're going to get a different amount of current. So here we would say I equals V over R. So that voltage across here is 0.5 volts over 175 ohms. So
It's like almost 3 milliamps. 2.8.
okay, 2.8 milliamps. So now we have 2.8 milliamps across 1.5 volts. So we can say our total is V total over I total. So that's V total is 2 volts now divided by 0. Yeah.
0.28.
Yeah, 0.028 amps. So what does the total resistance come out to be?
71.
71.5.
24. Yeah.
That's not okay. So we've got 2 volts over.
That's supposed to be 0.0.
Yeah, thank you. 0.002.
Oh, those are 2 different.
So 714 ohms. So so we have 175 there. So our D equals 714 minus 175. So that comes out to be what? 539. So in that case, the diode is acting like it has 539. Before it was 75. So it acts like it has different resistances in different cases.
So we cannot take any diode as a base when making calculations of total current or total resistance. Just only voltage would be, or
Right. You just always assume that it has the set voltage across
like
it.
we can't like use it to make a calculation as a main component because the resistance is not constant.
Right, well, you don't know the resistance, but you do know the voltage.
Yeah, that's the only thing pretty much I can use.
Right. Yeah, exactly.
Okay, that makes sense.
Okay, cool. Yeah. Other questions? Okay, cool. So we did a couple of examples from the homework.
Just one question about 10. So since it's a
Yeah.
forward bias diode, we assume 0.7 volts?
Yes, yes, exactly. Okay. So then, let's review the basic block diagram for power supplies. We talked about this last time. Let's go over that again. Remember, the goal of a power supply is to go from a high voltage AC signal to a lower voltage DC signal. Right, as little ripple as possible. So we want to go from here to there. What are some examples of real world power supplies? Where do we use power supplies in the real world? Oh.
Everywhere.
There you go. Pretty much. Yeah.
Anything you plug into the wall, pretty much.
Yeah,
Household
exactly.
voltage.
Any type of electronics. So yeah, power supply, phone chargers, computers, monitors. Pretty much all electronics runs on DC, and all the power that comes out of the wall is AC. So if you want to power something out of the wall, you have to go from AC to DC. Yeah, Jordan.
Is the generator automatically a DC?
Most generators are AC because they want to replicate the power that's coming out of the wall. But it is possible to make DC generators, but mostly they're AC.
So like gas motors?
Yeah, gas motor generators that you see they create AC power because they have little wall outlets, like, and so they want to replicate the type of power that's coming out of your wall.
Not to transfer back and forth.
Hmm?
So to avoid transferring from DC to AC, just straight AC.
Right. They create AC. Now, the AC that comes out doesn't look like a nice, pretty sine wave. It looks more like, it's ugly, but
It's a digital approximation of an AC signal.
yeah. So this is the goal of AC power supplies, to go from AC to DC. So the way that they get from AC to DC is they kind of sneak up on it, remember? So the first thing that they use, it's a transformer. And what is the goal of the transformer? Yeah, that's right, to lower the AC voltage. Remember, a transformer goes from one AC voltage to another one. We're trying to go from a high voltage AC to a low voltage DC source. So the first step is to go from high voltage AC to lower voltage AC. It's the same frequency, just the amplitude is small. So we got a transformer. And then what is the next component that we have in our power supply?
Rectifier.
Rectifier, yeah, exactly. And what does the rectifier do?
Gives us the
Cleans it up.
positive.
Yeah, it leaves us with only the positive part of our signal. And we saw last time that there are different kinds of rectifiers, and the signal that comes out can look a little bit different depending on which type you have, but with all rectifiers, the purpose is to take an AC signal and give you an output that only has positive parts, only positive voltages. then after that, we wanted to smooth out our signal a little bit. So what was the next part of the power supply? Yeah, a capacitor used as a filter. So the filter took our AC signal and it gave us a signal that looked more like that. Okay? So it's still not perfectly flat, but it is a lot smoother than these big humps that we had before. And what did we call this small change in the voltage from the top to the bottom here? Yeah. That was our ripple voltage, because it looks kind of like ripples on water. And was it better to have a lot of ripple or a small amount of ripple?
Small.
Yeah, a small amount, because right. Ideally, you'd have no ripples. DC signal is perfectly flat, perfectly smooth, so that has no ripples. So the less ripple you get, the better you are. Yeah.
If you add more capacitors, will it filter it better or
Yeah, in general, bigger capacitors,
bigger ones?
yeah. So more capacitance leads to better filtering, more smoothing, less ripple. The trade-off is that bigger capacitors take up more room, so you could end up with a really big power supply that could be kind of unwieldy if you use too much filter. But yeah,
Could you use like a few small ones instead of like one big one?
well, yes, yeah, but you
Still
still,
gonna be room.
the more you use, the more space it takes up. Yeah, but you're right, you could do that as well.
That's where they come out with regulator.
Right, and then, yeah, that's right, the last part,
Have to do a lot of capacitors probably.
yeah, exactly. So the regulator is the last part that goes from the slightly wavy signal to a nice flat DC signal. And it does help to smooth out those ripples, and the circuits are not too large, so they can do a pretty good job for you without taking up too much space. But I mean, the closer you can get for the regulator, the better you are. So this is the general block diagram of any power supply. Last time, I mean, we've already talked about transformers in 302. Last time we talked a little bit about rectifiers and filters. We'll review those again in a second. Tonight we're going to talk about regulators, some of the different kinds that are available, and you'll get to build power supplies that actually use different regulators. So let's review the rectifiers briefly. There were three kinds of rectifiers. Anybody remember one of those types?
Yeah, halfway.
Half wave, exactly. Yep, half wave. Full wave. And right. Perfect. Full wave. Good rectifier. So remember the half-wave rectifier, it was just a single diode, and it only captured the positive half of the signal. It didn't show it just got rid of the negative half. So that wasn't so great because it was kind of inefficient, right? If it's just throwing away half of your electricity, it's pretty inefficient. So that was okay, but it only used one diode. It was pretty simple, so it was it had that going for it. Fairly cheap, fairly inexpensive. So if you just get a cheap alarm clock from Walmart or something, it's probably going to have a half-wave rectifier. It's good enough in some cases. Full-wave rectifier, how many diodes did that one use?
Two.
Two, that's right. And it also used a special type of transformer. Do you remember what kind of transformer it had?
Center tap.
Yeah, center tap, that's right. So it had this extra wire on the transformer that it had to use. And so that's kind of a drawback because it turns out it's a little bit difficult to make transformers like that. You have to wind up the wire and then go back and scrape off some insulation and solder on a new wire. So that takes a little bit of time, and time is money, right? So transformers that have a center tap are a bit more expensive than normal transformers. So that's a full wave rectifier. Did it capture just the positive half, or did it capture both halves of the wave?
Both halves,
Both halves, that's right. So that's why we called it the full wave.
but then we didn't get as much voltage out.
Yeah, that's exactly right. Since we were using, that's right. The center tap cut the voltage in half, so the output was only half as much as it was with the half wave.
Final result the same halfway only
Yeah.
on the profit. I mean,
Well, yeah, on the profit. Yeah. So neither one of these is, well, the full wave is a bit more expensive. Yeah. Because it has that center tap. And then the full wave bridge rectifier, how many diodes did that one have?
4.
4, that's right. So that was the most complicated one in terms of the diodes, but it was kind of nice because it didn't have the center tap, right? And did it capture just half the wave or the full wave?
Full wave.
Full wave. So it was pretty efficient that way. So basically what it boils down to is that half-wave rectifiers are used sometimes in cheap electronics where they are good enough. Full-wave bridge rectifiers are used in more higher-end electronics that need a cleaner power supply. And then full-wave rectifiers are not used very much because they're more expensive and they don't give you quite as much voltage. Okay. So that's a brief review of the different types of rectifiers that we have. Then we already talked about filters. We said that more capacitors or larger value capacitors work to filter out the ripple more effectively than smaller capacitors. So any questions about the general block diagram of a power supply or the rectifiers? Okay, so then we talked about rectifier types. So tonight we're going to talk about the last component, the regulator. Okay, we're going to spend a little time about talking about different regulators and how they work. So we're going to talk about some integrated circuits that are used for regulators. We're going to talk about Zener Diodes, how they can be used, and then next time we'll touch on split mode power supplies. All right. So, a lot of things in electronics have really confusing names. You know, the numbers that mean hardly anything, right? 741 op amp, for example. The title means almost nothing. But fortunately, when it comes to voltage regulators, there's actually a convention that can be kind of useful that does have some meaning. So, okay. First of all, before we get into the names, let me tell you a little bit about what the regulator is. Okay. So we already said that it takes a ripple voltage and it converts it into a nice flat DC voltage. The package looks something like this. I'll pass this around in just a minute, but basically it is an integrated circuit like this. And it's got 3 legs. Yeah. So the order of the legs can be different on different ICs, but in general, you have input power on one of the legs, then you have ground, and then output power. Okay? So the input power is that wavy looking signal, and then the output power is that nice flat DC that we're looking for. Okay? So you hook up the input power to one of these legs, you hook up ground there, and then you get a nice flat DC signal coming out. Okay? So that's what it is. The way that it works is it uses something called feedback control. So basically inside here, it's got a little reference where it knows what voltage you're trying to create, and then it has a little bit of a variable resistor. And basically, if you have too much, well, basically inside there, it's a little variable resistor in a voltage divider circuit. So this resistor can change up here, and this one is fixed. And basically, if the output voltage is too high or too low, it changes this resistance until the output voltage is just right. Okay? So that's what's going on inside there. So it works pretty well, but it's not terribly efficient because basically if you have too much voltage, it's just taking some of that and turning it into heat. You'll notice that on the back of these, there's this metal plate, and that's called a heatsink. And you usually want to attach that to some larger piece of metal so that it can distribute that heat out, and the chip itself doesn't get too hot. So basically, it takes any extra voltage and just turns it into heat. So that's how they work. So I'll pass that around and take a look. Again, don't quote me on the exact order of these legs. It can vary from one chip to another. But this is the general. Each chip has an input power leg, a ground leg, and an output power leg. Okay? So that is the basic structure of what a regulator is, what it does, what a regulator chip does. There are different kinds of regulator chips. Some of them have a fixed voltage. So you can buy a 5-volt regulator that always puts out 5 volts, or a 9-volt regulator that always puts out 9 volts. You can buy them in all different varieties of fixed voltages. You can pick pretty much any voltage you want. Then there are other types of regulators that have a variable output. So you can buy one regulator and you can make an adjustment, and so you can turn the output voltage up or down. Okay? So let's get back to that naming that I was talking about a little bit. So I said that regulator names actually have some meaningful pattern that you can make sense out of. So they all start with 78. And then the last two numbers would be something like this. So if you got a 7805, that would be a 5-volt regulator. You got a 7809, that would be a 9-volt regulator. What do you think a 7812 would be?
12-volt regulator.
12 volt. So the last two numbers just specify the voltage that it has. Okay? So these are all positive regulators. So you put in a positive voltage, you get out a positive voltage. There are other types of fixed regulators that are in the 79 series. So 7905 gives you negative 5 volts. 7909, what do you think you get out?
9.
Negative 9 volts, exactly.
Thank you.
7912 gives you negative 12 volts. So these are all 79 series are negative regulators.
If you put a negative and a positive regulator in series,
Well,
0 volts.
yeah, yeah. So, I mean, you could put a positive regulator in and get a fixed 9 volts out or something, and then you could feed that into a negative regulator and then turn that positive 9 volts into a minus 5
we'll
volts.
change it over?
Yeah,
Wow.
you could switch it over.
That's cool.
I mean, it would be just like putting a nice flat 9 volts into a regulator.
Okay, I got you.
Yeah, but that brings me to another point. The input voltage always has to be higher than the output voltage, because this is like I said, a voltage divider inside. It can't create more voltage than it gets. So you always have to have a little bit more voltage going in than coming out. Thank you. So if you wanted to get out 5 volts, you would have to have, more like 7 volts going in, okay? So you always lose a little bit of voltage, and that extra voltage just gets turned into heat, like I said. So these are fixed positive and negative regulators, and then like I said, there are also variable regulators where you can adjust the output voltage to the level that you want. And we'll see both of those in tonight's lab. You'll get to play with a positive and a negative, and also a variable. And then it's also possible to create your own very simple regulator without using an integrated circuit at all. I think we mentioned this briefly a couple of classes ago. Yeah, Zener Diodes, exactly. So a Zener Diode always provides a fixed output voltage. So if you have an input voltage that's kind of wavy like this, then you can make a rectifier, or I'm sorry, a regulator that looks like this. So you've got your input voltage here that's kind of wavy like this, then your output voltage should be a nice flat fixed DC voltage, yeah.
So why would you want to use one versus the other?
Well, the the regulators are a little bit more efficient than the Zener diodes, and also they give you a slightly flatter output. So the output from the Zener diode would be mostly flat, but if you look really closely, you'd see some little tiny wiggles. Much better than the input, but still a little bit of wiggle. Whereas the output from the regulator should be very, very flat. And you'll actually get a chance to see both of them on the scope tonight, and you should be able to compare those.
Yes.
Yeah. On the other side, Zener diodes are pretty cheap. So if you just had a very simple circuit, then you could, and you didn't need a lot of power, then you could use a Zener diode. Also, Zener diodes are often used as references. So I think I mentioned inside of here, the regulator needs to know what voltage you're trying to get out. Normally, it figures that out with a little tiny Zener diode.
Oh.
So if you are trying to get 5 volts out, there's a little tiny Zener diode that's 5 volts in there built in, and it uses that as the desired signal, and then it adjusts this variable resistor up or down till the output voltage matches that output from the little Zener diode. Yeah. So that's what's happening there. Questions about that? All right. So we talked about regulator integrated circuits a little bit. We talked about Zener diodes. Next time we'll see that there's another type of regulator, which is a digital regulator, which can be used in a switch mode power supply. Okay, so those get turned on and off, and so instead of having a little resistor that just gets dialed up or down, you turn the output on and off and on and off and on and off really fast, and it kind of averages out to a nice flat signal. So we'll talk a little bit about that next time.
Oh, it's going to be so fast.
Yeah, really fast. Yeah. So any questions about that before we go and talk about our lab? Okay. So for the lab tonight, I wanted to briefly review electrolytic capacitors. So we're going to be using electrolytic capacitors as the filtering portion of our power supplies here. And electrolytic capacitors can explode if they get plugged in backwards. So let's take a minute and review. In a circuit diagram, an electrolytic capacitor is often shown like this, with one flat side and one curved side. So anybody remember which side of the capacitor is the positive side?
Flat.
Yeah, this is the positive side, and so this is the negative side. I always remember it, it's a silly thing, but you know those little Caesars commercials where you got the guy with the pizzas on the spear? So I think about the little guy here with his hand, and he's over here and holding up the spear with the pizzas on it.
And it's floppy.
Yeah, it's floppy, exactly. So the floppy pizza goes towards the ground. So anyway, so that's what's going on with electrolytic capacitors. If you look at the actual capacitor itself, what you'll see is it looks something like this, and it's got 2 legs coming out of the bottom of the capacitor, one like that and one like that. On one side of the capacitor, there is a strip that has a bunch of negative signs on it.
or what that means.
Right.
And they're not sideways, they're lengthwise with the capacitor, which is why I was going through those.
Yeah, exactly. So they can look like lines, or like a dotted line, but they're meant to represent negative signs. So the leg that's closer to the strip with the negative sides is the negative leg. The other one is the positive leg.
Okay.
So make sure that you watch out for this, and when you have an electrolytic capacitor, you plug it in the right way there. Okay. All right. Like I mentioned, tonight we get to use a bridge rectifier integrated circuit. So last time you had to build your own bridge rectifier with those four different diodes, and you had to put it all together. It was kind of tricky. But tonight we get to actually use this little integrated circuit that does it all for you. So let's see if we can find which one that is. Does anybody have the lab open?
7805.
Yeah, it should be 7805.
No, what's a 7805?
Oh. What are you talking about? The capacitor?
No, the bridge.
Oh, the bridge rectifier. It doesn't. Where does it say that at? Oh, okay. LM317.
LM317 or LM338 variable regulator.
No, those are variable regulators.
This.
So I think it's on the last.
Maybe it's on the last one because this also calls for 7805.
It's a diode bridge.
Huh, after that is homework.
Huh. No, you're right.
Shows an LM338 on the last page.
Maybe they.
Mine shows an LM. No? Wow.
Okay. Well, let me see.
What page is it on?
It starts on page 33, goes to 33.
Okay, well, I'm not seeing it right now. I'll take a look for it over the break, and then we can talk more about it afterwards. I do want to point out that we have half-watt resistors for this lab. So this calls for two 1 kilo ohm half-watt resistors. Okay, so the half-watt resistors they have the same color codes as the normal resistors, but they are about twice as big around. Okay, so be sure you use the bigger ones. If it looks like just a normal 1 kilo ohm resistor, that's not right. Make sure you get a bigger one. Okay, the bigger ones can withstand more current. They have more room to dissipate the heat, and so they can take the amount of current that we're going to be providing tonight. If you just get the normal small ones, they can burn up. Okay, so make sure you use the big half-watt resistors. All right. So, any questions about that?
Mm-hmm.
All right.
Are you going to go over the AC coupling on the scope, or are you
Oh,
going to
yes.
wait?
Thank you. I skipped right over that.
Yep.
So, the AC coupling on the scope, remember, there are two types of coupling. There's AC and there's DC. So, DC coupling shows us the entire signal just the way it is. So, if you have a 5-volt signal, it might show you something like that. And so it's often good to start in DC coupling so that you can get an idea of what your signal looks like. But sometimes you're not interested in the whole signal, all you're interested in is the little tiny wiggles that are going on way up here. Okay? So you want to zoom way in on those little tiny wiggles to be able to measure them more accurately. That's what we're going to be doing tonight when we measure the ripple voltage. So you could try and zoom in on the scope when the signal's like this, but what it's going to do is that it's going to zoom in on the part around 0. So you zoom in here, and then you have to adjust, and then zoom in and adjust, and go back and forth, and it's really difficult, and it's a pain. So instead of DC coupling, we can use something called AC coupling. AC coupling takes the signal and it gets rid of the average voltage. So you have the same signal, it has the same shape, but now it's centered right here around 0. So you can zoom way in on it, and you just keep getting closer and closer, and it stays right in the middle of your screen, and it's really easy to see. So you want to use AC coupling when you're just interested in the wiggles. That's called the AC part of the signal. So the way that you get to AC coupling on the scope is that if you're looking at the scope, you've got the main screen there, and then you've got the different channel buttons. So right here, it says channel 1, for instance. So you would push channel 1, and then up here, it would say DC, and there's a little button next to there. So if you push that button, it cycles through the different types of coupling. So if you push it, it starts out in DC, you push it, it goes to AC, and you push it again, and it goes to ground, which just gives you a flat signal. And you push it again, and it cycles back through DC, and so on and so forth. Okay? So again, to change the type of coupling, you push the channel button, then you push this button to cycle through and pick the type of coupling you want.
Okay.
Questions about that? Okay. Cool. So that's what I wanted to say. You guys are welcome to take a short break, or you can just get started on the lab now. It's up to you.